Effects of overweight on the spinal biomechanics. The WHO called being overweight and obesity the leading chronic health problems. In the world, more than 1.9 billion adults, 18 years and older, were overweight in 2014, and of these over 600 million were obese. Overweight and obesity are contributing factors for many ailments and can lead to the development of chronic diseases, like diabetes, cardiovascular disease, coronary heart disease, or osteoarthritis. While there are a large number of studies on the effects of these factors on the cardiovascular system and the psyche of the concerned person, the potential consequences of orthopedic damage, particularly of the spine, associated with obesity are hardly known yet. A direct correlation between back pain and obesity is described. The exact load changes within the various spinal structures have not been sufficiently explored yet. With the help of computer modeling, the effects of obesity on the kinematics and kinetics of various spine structures can be analyzed. In the following, the potential effects of obesity of an adult and an adolescent human are illustrated by specific MBS models exemplary. Example 1. Simulation of the effects on the spinal structures of body weight of a normal weight and an overweight adult male. The modeling was carried out in 3 steps. Step 1 is the creation of an MBS model of the lumbar spine. Step 2, the creation of a suitable surface models of the 2 weight classes, including the determination of their anthropometric characteristics, and Step 3, the fusion of the MBS lumbar spine model with the surface model. In this example, the force application point is also located in the center of gravity. Taking into account the body weight, body height, 1.85 meters, sex, male, age, 37, and the original 2 surface models, a normal weight man, 75 kilograms, and an obese man, 127 kilograms, grade 2, are created with the help of an open-source software for the creation of human 3D surfaces. By means of the mass distribution model of Zatsiorsky, the mass distribution of the individual body segments is determined. All other model parameters are identical in both models. By fusing the surface models with the detailed biomechanical model of the lumbar spine, 2 new simulation models are built up, so that the effects of a normal weight and obese man on the spinal structures can be analyzed. Due to the body weight, the intervertebral discs are deformed. In the case of the normal weight person, in general the intervertebral deformations in all FSUs are very small. The cranial-located intervertebral discs are more deformed than the caudal intervertebral discs. Comparing the deformation values of the obese with those of normal weight, it can be seen that they are about 1.7 times greater. The validation of the deformation values is difficult, because we are not aware of studies, whose study design corresponds exactly to ours. Brinkman investigated the fatigue fracture of human lumbar vertebra under cyclic axial compression and presented an example of force versus deformation curve of a specimen with material properties characterized as tough. The force versus deformation curve indicates that a force of 500 N causes a deformation of about 0.025 cm and a force of 750 in a deformation of 0.044 cm. Because the simulated acting weight force of the upper body segments is in the case of normal body weight approximately 460 N, and in the case of overweight approximately 780 N, and the deformations are in the range of 0.025 cm to 0.04 cm, normal weight, and between 0.042 cm and 0.068 cm, obese, it is seen that the magnitude of this values corresponds to those of Brinkman. Deformations of the intervertebral discs. Each intervertebral disc develops a disc force, which depends on the deformation and deformation velocity of the corresponding FSU. Shows the force component acting perpendicular to the disc. It can be clearly seen that the intervertebral discs of the obese are much more stressed than those of normal weight. The intervertebral disc force of the obese is, as well as in the above discussed case of deformation, 1.7 times higher than the intervertebral disc force of the normal weighted. It could therefore be concluded that the deformation value, as opposed to the deformation velocity, see section 3.3, has a great impact on the intervertebral disc force. Intervertebral disc force of the different FSUs. Shows the intersegmental rotations of the intervertebral discs. Whereas all intervertebral discs of the obese person perform flexions, the intervertebral discs of the normal weight person are deflected in different directions. The lowest 2 intervertebral discs of normal weight person perform flexion. The FSU L4, L3 and L2, L1 rotate backwards and the uppermost FSU L2, L1 rotates forward. Particularly evident is the high rotation values of the obese person. The FSU L1, L2 performs with about 17 degrees, the largest rotational movement. In the literature, the maximum range of motion, ROM, of FSU L1, L2 is specified by values between 2 and 13 degrees. Consequently, our simulation values differ from these values. But the difference is relativized by the therein given standard deviations of about 2.5 degrees. Further, it has to be analyzed whether the model of the obese person sufficiently reflects the reality, because identical biomechanical parameters are used in both simulation models. It is necessary to investigate in further work whether the biomechanical properties of the spinal structures are adapted in reality to the body weight, in order to avoid such rotations and prevent overloading or degenerative damage. Moreover, in this model, the stabilizing muscles are not considered, which could prevent such rotation. Intervertebral rotations of the different FSUs, positive rotation angles represent flexion and negative rotation angles extension movements. The movements of the FSUs can affect the biomechanical behavior of posterior located facet joints. It is striking that the loads of the FSU L1, L2 respectively L2, L3 are not loaded. Further, it can be seen, that in the case of obesity the loads decrease to cranial. A possible reason may be, in this section, the pure ventral directed rotations. The two corresponding joint surfaces of the facets are distracted, and thus no contact force is built. To achieve a complete clarification of this, a model specification in the form of a sophisticated 3D facet joints modeling is required, see section 5. Contact forces of the facet joints. Example 2, simulation of the effects on the spinal structures of body weight of a normal weight, an overweight, and an obese child. More than 42 million children under the age of 5 were overweight in 2013 worldwide. According to Deckelbaum, not only in the USA the number of overweight children and adolescents has doubled in the last 2 to 3 decades, but also the similar doubling rates are being observed worldwide. Therefore, the WHO called overweight and obesity as the leading chronic health problem. 3 MBS models of the child's lumbar spine were created to quantify the effects of normal weight, overweight, and obese children to the kinematics and transmitted forces and torques of the different spinal structures. With the help of these 3D models, dynamic movements in static situations can be simulated. For simulation and load calculation of the effects of different weight classes, the masses of the body segments are adapted to these weight classes. Therefore, the first lumbar vertebra L1 is loaded with the weight of the upper body segments of a normal weight, an overweight, and an obese child in different simulations. The total mass fractions of the segment parts is normal equals 22.91 kilograms for normal weight child, mover weight equals 27.73 kilograms for overweight child, and obese equals 32.56 kilograms for obese child. In the case of overweight and obesity, the intervertebral discs are more heavily loaded in comparison to the normal weight child. In both cases, the intervertebral discs of the FSU L4, L5 are most loaded. The slightest load undergoes the FSU L1, L2. The increase in body weight has a direct influence on the loading structure of the intervertebral discs. If the normal weight child would become overweight, the loads of the intervertebral discs would rise by an average of 1.5 times. In the case of obesity, the intervertebral discs are more than 2.3 times higher loaded. Percentage load of the intervertebral disc. Through the increased body weight, the intervertebral discs perform pure flexion. Here, the amount of flexion of the obese child is mostly more than doubled compared with the movement of the normal weight child. Particularly obvious is the difference in the FSU L3, L4. In the case of obesity, this FSU is deflected more than 3.5 times larger from its initial position, normal weight. Percentage intersegmental rotation. Through the forward rotations of the intervertebral discs, the approach and origin points of the posterior ligaments move away from each other. As a result, the corresponding ligaments are stretched and develop in an opposite direction, acting as reaction force. In the case of an obese child, the posterior ligaments are 2 to 2.5 times more loaded than under normal body weight. Under obesity, a particularly extreme ligament load occurs in the FSU L3, L4. This more than 4 times larger load may result from the above described extensive intersegmental rotations in these FSU. Percentage load of the posterior ligaments.